We've done this before in class, but I do want to talk about some of the things I saw missing in these work for both B and C. Namely, this idea that when we're talking about closure under vector addition and closure under scalar multiplication, we need to be really clear that we are starting with a vector from our subset, from our potential subspace. So first things first, we should choose, since we're proving it's not a subspace, we need just a single example of either failing closure under vector addition or failing closure under scalar multiplication. We could also show that the zero vector is not in our space. However, because this is set up as a homogeneous equation, right? We could set this equal to 0. If every variable here was 0, this would equal 0. That's not going to be a problem. So no reason for me to test the zero vector. I can already see the zero vector is in Q. So we need to choose, though, some vector inside of Q. So I like scalar multiplication because I like to find one vector instead of Q, and that's typically a challenge of itself, right? And so in this case, if I'm choosing this, I'm going to look at, first off, I want to set something as my Y, because Y is the most going on here. It's going to be easier to define the other two after. The other thing I want to notice about this Y is that Y is squared. This is where my problem is going to come in, right? If I take a number and I do my scalar multiplication before squaring versus after squaring, these are not the same thing. And so this is where I'm going to see my failure under scalar multiplication. It would be true for vector addition as well, right? If I took some y1 plus some y2 and squared it, that's not going to be the same thing as taking both those things and squaring them. This is where my failure is going to come in. So I want to choose a value of y where I'm going to be able to see this. So I should not choose 0. So let's just go ahead and start by like, okay, let's try 1 for our y. So right now I'm at a -4. And now I also have to choose something for x. Now here's the deal. Depending what I choose for x, I could make my life harder in terms of z. I might have a fraction. It's not a big deal, but in general, I might want to try to do something, shoot for something where z is going to work out nicely. So I could see here, if I choose -1 for my x, then I'll get a -4 times a -1. I'll have a +4, which means my z is equal to 0. So that is a pretty nice vector to use. I could have also tried to make sure I subtracted off 4 more -4s. So I could do something like 1 and a 4 here. That would have been, instead of this, I would have had a -16, which is -20. And so I would have had a nice z as well using that. But you have to be a little bit clever if you don't want to end up with fractions. Now that I'm here, here's the piece that a lot of students are missing. I want something to say, hey, look, I have chosen a vector in Q, right? This is the whole point of closure, that if I have some vector in my subset, if I multiply that vector by a scalar or I add that vector to another vector from my subset, I should still stay in my subset if I am in a subspace, right? And so I'll go, okay. I liked it also, like I said, to be able to be like, okay, -4 times 1 squared minus 4 times -1 is equal to 5 times 0. Oops. This was just me being happy because now I said, aha. We checked that it's in Q. That's the verification that it's in Q. You don't need that. In fact, what I was seeing from some students was doing some stuff with, I'll just do it in red, trying to use their set notation. We just want a single vector here. There's no reason to use a set notation at all, or doing something with that conditional piece, that line that's such that. Let's not. We just want to say, okay, this thing is in Q. And so we just need to choose any C. So let's try 2 times this. And we want to show this is not in Q. That's our goal. And that's easy enough. We just need to show that it fails our condition. So we want to show that -2, 2, 0 does not give us this same condition. So if I do this, -4 times 2 minus 4 times a -2 is equal to 5 times 0. I have -16 plus 8 is equal to 0. This is not true. Now, we've got a lot of stuff. We haven't written a conclusion, so we want to say something along the lines of Q is not a subspace as it fails closure under scalar multiplication. And if we want to provide our evidence here, we'd have something like -1, 0, 1 is within Q, but 2, -1, 1, 0 is not in Q. Right, that's what we just found. So that's the whole goal of this section right here, is just choose something in Q, ensure that you have told me that it is in Q. If you don't say that, what are we even doing here? Show me that either when you add it to another vector in Q or you multiply it by a scalar, we break out of this space and therefore we fail that closure under whichever the two things you decided to test. If you decide to use X, Y, Z's, if you decide to come up here, you need to be really clear about what C's it fails for. Because most of the time when students wrote this, I went, well, this is true for C is equal to 0, for C is equal to 1, right? There are a number of things that actually does hold for. In fact, it holds for Y is equal to 0, right? Like, so just be really clear. It's so much easier to choose one example and show with numbers that it's not true than to communicate why these two mathematical expressions are not equal to each other. If you are going to show that two mathematical expressions are equal to each other, you're going to have to probably state which cases that is true for, because otherwise it is true sometimes. And so you can't just say it's not equal to. You can just say it's not equal to certain values, whatever those might be. Right? The second one, if you did vector addition here, this will be true as long as y1 and y2 are both not, like neither one is equal to 0, right? That's what we'd need to make that second one true.